Okay, welcome to another video. I was making really good progress doing a lot of really fun things. So I want to continue that. We're going to code along with the book, but we're going to use a totally different project than they're doing. We're going to blend this in with network engineering. We're going to write a program kind of like Ansible or something like that, but it's just going to be custom written, and it's going to take in the business needs of the, it's going to configure a topology according to the business needs, and we're gonna just assume that the business needs align with this Cisco design guide. In our case, we're gonna just have a campus LAN and wireless LAN business, but there are other kinds of designs. Okay, so if we go to all guides here, now we can get design guides by category. So we can get networking or data center. Here's a good one for big data. That might be an interesting one to look at. The one we're going to do though is this one here, but I would like to do multiple different kinds of designs to have the code be able to support multiple types of designs, not just one design. We got 34 results here, but it's not letting me skip down. Okay, there we go. Well, okay. All right. Let's okay, but let me not get distracted here. I was just looking at the other kinds of designs because this campus wired and wireless design is I think it's a good place to start, but there are other designs that I think would be more interesting. This evolved programmable network I think would be really interesting. Yeah, and then data center, of course, that's going to be interesting as well. But we're just going to stick to the perhaps least interesting one for now. So let me jump to the bookmark where I left off. Okay, and let's begin to read about layering. Encapsulation and abstraction help us by hiding details and protecting the consistency of our data. But we also need to pay attention to the interactions between our objects and functions. When one function, module, or object uses another, we say that one depends on the other. These dependencies form a kind of network or graph. In a big ball of mud, the dependencies are out of control. As you saw in a real-life dependency diagram, source Enterprise Dependency, Big Ball of Yarn, by Alex Papadimoulis. Changing one node of the so they're talking about, I remember that. Yep, they're talking about this where each node has multiple dependencies on other nodes. Changing one node of the graph becomes difficult because it has the potential to affect many other parts of the system. Layered architectures are one way of tackling this problem. In a layered architecture, we divide our code into discrete categories or roles, and we introduce rules about which categories of code can call each other. One of the most common examples is the three-layered architecture shown in layered architecture. So it looks like these links are just, they're just links to the graphic. So here we have the presentation layer, then the business logic layer, and last the database layer. So it's kind of like the OSI model. Please do not take sausage pizza away. Presentation, data link, network, transport, session, presentation, and application. Similar to that, it's got we're abstracting it out into layers, and then so that way you don't need to think about everything all at once. You can break it down and think only of the relevant parts at a single time. Layered architecture is perhaps the most common pattern for building business software. In this model, we have user interface components, which could be a web page, an API, or a command line. These user interface components communicate with a business logic layer that contains our business rules and our workflows. And finally, we have a database layer that's responsible for storing and retrieving data. For the rest of this book, we're going to be systematically turning this model inside out by obeying one simple principle. Oh, well, why are they going to do that? I thought this was a good way to do it. So this is the most common way to do it. So I guess the most common way to do it is not the best way to do it. So it looks like this book is going to teach a way that's uncommon, which might be a little bit hard because convincing people to use an uncommon architecture might be difficult, and then people's experience, they won't have experience with this, they'll have experience with a more common architecture. But that's okay, if it works better and it's clearly better than the common way of doing it, that is totally fine with me. I have no objection to it. So we're going to be systematically turning the layered architecture model inside out, and we're going to do that by obeying one simple principle, and that is the dependency inversion principle. You might be familiar with the dependency inversion principle, or DIP, already, because it's the D in solid, S-O-L-I-D. I am not familiar with any of that at all. Unfortunately, we can't illustrate DIP by using 3 tiny code listings as we did for encapsulation. However, the whole of part 1 is essentially a worked example of implementing the DIP, dependency inversion principle, throughout an application. So you'll get your fill of concrete examples. In the meantime, we can talk about DIP, dependency inversion principles. Formal definition. Number 1, high-level modules should not depend on low-level modules. Both should depend on abstractions. And number 2, abstractions should not depend on details. Instead, details should depend on abstractions. So I think I'm going to highlight this as my first note, because I think that's going to be valuable. Okay, so let's make a note here. We're going to say the principal is a person. It's your pal. Principal is your pal. So this is an idea. Okay, so this is my first note, the definition of the dependency inversion principle. That's going to be something really important to the rest of the book going forward. All it means is that the high-level modules should not depend on low-level modules. Instead, they should depend on abstractions. And abstractions should not depend on details. Instead, details should depend on abstractions. So I'm not exactly sure what that means now, but that's going to be what they explain next. But what does this mean? Let's take it bit by bit. High-level modules are the code that your organization really cares about. Perhaps you work for a pharmaceutical company and your high-level modules deal with patients and trials. Perhaps you work for a bank and your high-level modules manage trades and exchanges. The high-level modules of a software system are the functions, classes, and packages that deal with our real-world concepts. By contrast, low-level modules are the code that your organization doesn't care about. It's unlikely that your HR department gets excited about file systems or network sockets. It's not often that you discuss SMTP, HTTP, or AMQP with your finance team. For our non-technical stakeholders, these low-level concepts aren't interesting or relevant. All they care about is whether the high-level concepts work correctly. If payroll runs on time, your business is unlikely to care whether that's a cron job or a transient function running on Kubernetes. Depends on doesn't mean imports or calls necessarily, but rather a more general idea that one module knows about or needs another module. And we've mentioned abstractions already. They're simplified interfaces that encapsulate behavior in the way that our DuckDuckGo module encapsulated a search engine's API. All problems in computer science can be solved by adding another level of indirection. I'm not sure what indirection means. So the first part of the dependency inversion principle says that our business code shouldn't depend on technical details. Instead, both should use abstractions. Why? Broadly because we want to be able to change them independently of each other. High-level modules should be easy to change in response to business needs. Low-level modules, details, are often in practice harder to change. So this is perfect because this is exactly what I wanted, why I'm reading this book, because the problem I've been having with my Python projects is like, you know, the most important thing in writing a piece of code is having it do what is expected to do or what people want you to write it and accomplish. But I found the biggest problem with that is that it changes what people want from you. And for me, like, that's been like really frustrating to me because like I'll have spent time writing something and then by the time I'm finished and I've got it out the door, I needed to have written something else. And you know, from certain learn to code programs, they would say, oh, that's my fault because I didn't gather the requirements correctly. But the problem I've been having is I did the best I could. Yes, I gathered all the requirements. This is what I was told this needed to do. But by the time I'm finishing, that changed. So a big reason I'm reading this book is because I want my code to have the ability to pivot, to change. And I don't want that to be called scope creep or creep or for that to be a negative thing. I want my code to be flexible and to adapt and to be able to handle new and changing requirements. So I'm really happy this book brings this up. Think about refactoring to change a function name versus defining, testing, and deploying a database migration to change a column name. We don't want business logic changes to slow down because they are closely coupled to low-level infrastructure details. But similarly, it is important to be able to change your infrastructure details when you need to. Think about sharding a database, for example, without needing to make changes to your business layer. Adding an abstraction between them, the famous extra layer of indirection, allows the two to change more independently of each other. The second part is even more mysterious. Abstractions should not depend on details. Seems clear enough, but details should not depend on abstractions is hard to imagine. How can we have an abstraction that doesn't depend on the details it's abstracting? By the time we get to Chapter 4, Service Layer, we'll have a concrete example that should make this all a bit clearer, or concrete. I don't know if there's a difference between concrete and concrete. I know they're spelled the same, but can you say concrete when you mean concrete? Or do you have to say concrete if you mean concrete, and concrete if you mean concrete? Or can you say concrete when you mean concrete, and concrete when you mean concrete? I don't know. A place for all our business logic, the domain model. But before we can turn our three-layered architecture inside out, we need to talk more about that middle layer, the high-level modules or business logic. One of the most common reasons that our designs go wrong is that business logic becomes spread throughout the layers of our application, making it hard to identify, understand, and change. And that's the biggest problem I have in my coding is, as I said, when things, just even understanding, just having that business logic integrated through every aspect of the application, so that when things change, oops, I've got to change it here, there, everywhere, and not only that, it's hard to see what it was before and do a diff between what it is now. So perfect. I'm so glad I switched to this book. Sunk costs is a horrible fallacy. Don't fall into it. I thankfully did not fall into it too badly. Chapter 1 domain model shows how to build a business layer with a domain model pattern. The rest of the patterns in part 1 show how we can keep the domain model easy to change and free of low-level concerns by choosing the right abstractions and continuously applying the dependency inversion principle. So one clarification, anyone who hasn't watched my other series, I was doing a series called Python for DevOps, and I read 3 chapters in a row that just weren't offering me up anything valuable, that had typos all over it, and that I couldn't get any of the code examples to work, because in one code example they were saying to pass a single argument to a function that had 2 parameters defined. So what normal people would do, what the average person would do, and what I probably used to do, is just say, okay, well, you know what, I bought this book, I already read half of it, let's just keep reading the rest of it. But that's something that's called a sunk cost fallacy, I think. Correct me if I'm wrong in the comments, but sometimes a better action, now of course the book can get better if you keep reading it, so that it is possible, but sometimes it is actually better to stop reading it and move and do something that you know is going to be more valuable for you. And that's what I decided to do. I stopped reading the book, and I switched over, and now I'm reading this book instead. And so far, I'm really happy with that decision. Okay, so we're on to part 1, building an architecture to support domain modeling. Most developers have never seen a domain model, only a data model. Most developers we talk to about architecture have a nagging sense that things could be better. That's hilarious. They're often trying to rescue. Now, I wonder if the authors of this book believe that their architectures in here could be better. They are often trying to rescue a system that has gone wrong somehow and are trying to put some structure back into a ball of mud. They know that their business logic shouldn't be spread all over the place, but they have no idea how to fix it. We found that many developers, when asked to design a new system, will immediately start to build a database schema, and with the object model treated as an afterthought. This is where it all starts to go wrong. Instead, behavior should come first and drive our storage requirements. After all, our customers don't care about the data model. They care about what the system does. Otherwise, they just use a spreadsheet. So I'm going to highlight this. Behavior should come first and drive our storage requirements. So we'll copy that. We'll do a duplicate here, and then we're gonna fill it in here. Okay, and now we've got this highlighted, so we'll do okay, we'll make this a hyperlink. In a new window, apply. Perfect. Okay. Yeah, I'm going to do as many hyperlinks as I can. It just looks a little bit nicer. There's no reason not to have it. And it looks a little bit nicer. Okay, yeah, these notes look really nice. And then I really like having it like this so that I can, yeah, okay. Perfect. The first part of the book looks at how to build a rich object model through TDD, which we remember stands for task-driven development. In Chapter 1, Domain Model. What does TDD stand for? Oh, test-driven development. That makes sense. Okay, I was close. I knew it was driven development. But, and task is actually kind of close, because task means you're like doing it, well, I don't know. Task really just is, test is the right thing. In Chapter 1, Domain Model, and then we'll show how to keep that model decoupled from technical concerns. We show how to build persistence ignorant code and how to create stable APIs around our domain so that we can refactor aggressively. To do that, we present 4 key design patterns. The repository pattern, an abstraction over the idea of persistent storage. The service layer pattern to clearly define where our storage use cases begin and end. The unit of work pattern to provide atomic operations, the aggregate pattern, to enforce the integrity of our data. If you'd like a picture of where we're going, take a look at a component diagram for our app at the end of building an architecture to support domain modeling. And don't worry if none of it makes sense yet. We introduce each box in the figure one by one throughout this part of the book. Perfect. This is exactly what I've been wanting to do. Like, I've been wanting to draw these diagrams for my code, but like, I've just like often felt that like the diagram just wasn't that useful. Like I didn't know how to draw a diagram that would lead to a well-designed piece of software. Like I obviously know how to draw a diagram, but I don't know how to draw a diagram that helps me write code better. I know how to draw a diagram, and I can just draw any diagram, but how to draw one that helps me build better code is why I'm reading this book. Now I'm going to highlight this. These are 4 key design patterns, and add that as a note as well. I'm going to duplicate this. Okay, and I think I'm going to have my notes go into bullet points. Okay, and then obviously it's going to be, I wish I could add bullet points at the top instead of the bottom. I think I can if I just, yeah, so now I can do test 1 2 3, and then when I'm done with that, I can do a jump to the front, and then my next bullet point can be at the top instead of the bottom. So as I'm taking notes, it goes down and down and down, and I don't have to scroll. Okay, so yeah, we're ready to go. Update. Okay, so here's, perfect. So we've got the service layer, the domain. I don't see the other layers. I only see one layer, and I thought they were going to abandon the layer approach. But yeah, we can see Flask invoked services, which start a unit of work, which provide a repository, and this is an adapter. It commits changes to the database, and it loads and saves to the domain. So services, in addition to starting a unit of work, it calls methods on the domain. We also take a little time to talk about coupling and abstractions, illustrating it with a simple example that shows how and why we choose our abstractions. 3 appendices are further explorations of the content from part 1. Appendix project structure is a write-up of the infrastructure for our code, for our example code, how we build and run the Docker images, where we manage configuration info, and how we run different types of tests. Appendix CSVS is a proof in the pudding kind of context. Proof is in the pudding, showing how easy it is to swap out our entire infrastructure, Flask API and ORM and PostGRES for a totally different I/O model involving a CLI and CVSs. Finally, Appendix Django may be of interest if you're wondering how these patterns might look if using Django instead of Flask and SQL Alchemy. All right, next part is domain modeling. This chapter looks into how we can model business processes with code in a way that's highly compatible with test-driven development. We discuss why domain modeling matters, and we'll look at a few key patterns for modeling domains: entity, value object, and domain service. A placeholder illustration of our domain model is a simple visual placeholder for our domain model pattern. We'll fill in some details in this chapter, and as we move on to other chapters, we'll build things around the domain model, but you should always be able to find these little shapes at the core. So, perfect. Here's a good. So so you can start with this and then work it out for your project. What is a domain model? In the introduction, we used the term business logic layer to describe the central layer of a three-layered architecture. For the rest of the book, we're going to use the term domain model instead. This is a term from the DDD, domain-driven development community that does a better job of capturing our intended meaning. See the next sidebar for more on DDD. The domain is a fancy way of saying the problem you're trying to solve. Your authors currently work for an online retailer of furniture. Depending on which system you're talking about, the domain might be purchasing and procurement, or product design, or logistics and delivery. Most programmers spend their days trying to improve or automate business processes. The domain is the set of activities that those processes support. A model is a map of a process or phenomenon that captures a useful property. Humans are exceptionally good at producing models of things in their heads. For example, when someone throws a ball toward you, you're able to predict its movement almost unconsciously because you have a model of the way objects move in space. Your model isn't perfect by any means. Humans have terrible intuitions about how objects behave at near light speeds or in a vacuum because our model was never designed to cover those cases. That doesn't mean the model is wrong, but it does mean that some predictions fall outside of its domain. Yeah, that's a really good way to say it. Is like Newtonian physics, like a lot of science isn't meant to always be true no matter what. It's meant to explain certain phenomenon in certain cases. So like if a mathematical equation, for example, force equals mass times acceleration, I think that's always going to be true, but like what if your mass is really, really small or really, really big? I think if your mass is small enough, or like what if your mass is 0? Yeah, like if your mass is 0, I think you can still have force. So like, can you have force when the mass is 0? Oh, okay. It's net force, not force. Yeah, I remember this from a long time ago, but it's yeah, okay. But let me read this again because I found this pretty impactful. Um, so humans have terrible intuitions about how objects behave at near light speeds or in a vacuum because our model was never designed to cover those cases. That doesn't mean the model is wrong and that it won't work in cases where it was designed to cover, but it does mean that some predictions fall outside of its domain. Love it. Thank you. The domain model is the mental map that business owners have of their businesses. All business people have these mental maps. They're how humans think about complex processes. You can tell when they're navigating these maps because they use business speak. Jargon arises naturally among people who are collaborating on complex systems. Imagine that you, our unfortunate reader, were suddenly transported light years away from Earth on board an alien spaceship with your friends and family and had to figure out from first principles how to navigate home. In your next few days, you might just push buttons randomly, but soon you'd learn which buttons did what so that you could give one another instructions. Press the red button near the flashing doohickey and then throw that big lever over by the radar gizmo, you might say. So first principles, they didn't give a definition for that. I'm going to give my own definition without looking it up and then see how it is different from what the official Wikipedia or whatever I find defines it. So my own definition of first principles without looking it up are basically the most basic and simple and true thing you can say that doesn't depend on anything else being true. So if you were transported light years away from Earth and you are on an alien spaceship and you had to figure out how to navigate home, so using first principles, I think the first thing you would do is actually verify that you weren't home somehow, actually verify that you were on a ship somehow, verify that the laws of physics more or less are the same, and then verify that, and then try to figure out like where you were, because I think one mistake you could make if you weren't operating from first principles is you could assume that you've been transported light years away from Earth in a certain direction, and then you can say, oh, well, we've been transported light years away from Earth, so we know we got to go to the left, because when we're transported away from Earth, we're always transported away to the right of Earth, further from the sun. Like, so if here's the sun and here's the Earth, if you're figuring out without using first principles, you might make a mistake and say, when we're transported light years away from Earth, we're always going out from the sun like that. And of course, it gets complicated because the Earth is rotating the sun, so you can't like whichever direction you point out, it could be that direction, could not. So it gets complicated, but from first principles, navigating home from a spot you had been transported to, you would need to determine where you were. If you weren't using first principles, you could just focus on how to get home and not do more simple verifications. All right, let's see how that explanation differs from what I find online. So a first principle is a foundational proposition or assumption that stands alone. We cannot deduce first principles from any other proposition or assumption. Aristotle, writing on first principles, said, "Reasoning by first principles removes the impunity of assumptions and conventions." All right, let's see another one. So here's a good one from Wikipedia. A first principle is a basic proposition or assumption that cannot be reduced from any other proposition or assumption. In philosophy, first principles are from first cause attitudes and taught by Aristotelians, and nuanced versions of first principles are referred to as postulates by Kantians. So let's see an example of a first principle. Here we go. Here's an example. So this is an example in formal logic. In a formal logical system, that is a set of propositions that are consistent with one another, it is possible that some of the statements can be deduced from other statements. For example, the syllogism. A syllogism is basically a logical argument. All men are mortal. Socrates is a man. Socrates is mortal. The last claim can be deduced from the two. So these, the first principle is an axiom that cannot be deduced from any other within that system. So these two here are first principles, that all men are mortal and that Socrates is a man. Socrates being mortal, that's not a first principle, because you need to know that Socrates is a man, and you need to know that all men are mortal in order to know that Socrates is mortal. It depends on other information. So I guess a more clear definition of a first principle, kind of different from how I explained it, is it's information that doesn't depend on the knowledge of other information. Yeah, and I'm going to stop there. I'm going to actually write that in my note. Yeah. Okay, I think that's a really simple definition for what a first principle is. It's information that doesn't depend on other information. So that's the kind of stuff you really want to focus on, because once you have all of that information, you can build up the rest of it. So that example, all men are mortal, Socrates is a man. Once you have those two things, you know that Socrates is mortal. If you didn't know that Socrates was a man, or you didn't know that all men were mortal, you wouldn't know that Socrates was mortal. So if I told you all men are mortal and Socrates is mortal, you actually wouldn't know if Socrates was mortal or not, because you wouldn't know if Socrates was a man or a woman. So that's why it's so important to focus on first principles, because you need the first principles in order to have everything else, and in order to know that everything else is accurate. Sure, I can just tell you Socrates is mortal, and there you go, you have it. Socrates is mortal, but then you're kind of stuck. You don't know anything else about Socrates. So you're kind of in a little bit of a informational wasteland or desert. But if instead I were to tell you all men are mortal, Socrates is a man, now you know the same information you would have known before if I had just told you that Socrates was mortal, but you know it because of these two other pieces of information which can be used to learn more things, just those things. So for example, if I introduce you to Socrates' wife, now without any extra information at all, you know that Socrates' wife is not immortal, because she is, in this example, female. In your first few days, you might just push buttons randomly, but soon you'd learn which buttons did what, so that you could give, so I read that part already, next part. Within a couple of weeks, you'd become more precise as you adopted words to describe the ship's function. Increase oxygen levels in cargo bay 3, or turn on the little thrusters. After a few months, you'd have adopted language for entire complex processes. Start landing sequence or prepare for warp. This process would happen quite naturally without any formal effort to build a shared glossary. So this is not a domain-driven design book. You should read a domain-driven design book. Domain-driven design, or DDD, popularized the concept of domain modeling. And it's been a hugely successful movement in transforming the way people design software by focusing on the core business domain. Many of the architecture patterns that we cover in this book, including entity, aggregate, value object, see chapter 7 aggregate, and repository in the next chapter, come from the DDD transition. In a nutshell, DDD says that the most important thing about software is that it provides a useful model of a problem. If we get that model right, our software delivers value and makes new things possible. If we get the model wrong, it becomes an obstacle to be worked around. In this book, we can show the basics of building a domain model and building an architecture around it that leaves the model as free as possible from external constraints so that it's easy to evolve and change. But there's a lot more to domain-driven design and to the processes, tools, and techniques for developing a domain model. We hope to give you a taste of it, though, and cannot encourage you enough to go on and read a proper DDD book. So, looks like they really like this publishing company. I wonder if they're the same. But let's save these in this further reading, and let's do one better than that, and we'll go and see if we can find a free copy of it, and then move on to that book next. So we'll do a paste as plain text. Oops, but we still got red text for some reason. So can I clear formatting? I can. Okay, sweet. Okay, so let's just clear formatting on everything. I wonder if that'll clear my links though. Okay, it looks like it didn't. Okay, you know what? We can get rid of this here and just put the bookmark at the top. Perfect, and then we can put the notes here. There we go. And then we do want some formatting. We want the, yep, we want that. Okay, and we want a blank one for new notes. Okay, and then here we want the further reading, so we'll put that in bold, put this in bold as well, and that can be in title case instead of, so that the only thing in uppercase is my bookmark. That makes it easier to see. Okay. So now we've got the red book here, and then we've got the original blue book. So let's get rid of this, make that shorter. Okay, now let's see if we can find a free copy of these books and then link to it the same way we found one here. Oh, let's do a cancel, save that first, the most important thing. So, oops, it looks like when I created my link here, I did not tell it to, oh, okay, yeah, there we go. Okay, there we go. Now it opens up in a new tab. I'm going to update that. Oops, looks like it actually, my link got screwed up, so let's just remove it. And then we can save that. Okay, how do I get rid of, okay, I can click this, I think. Shoot, this is not working the way I wanted it to. Shoot. Oh, here we go. Perfect, okay. So I can highlight it, and then I can click the, yeah, so here as well, I can do the same thing. There we go, and now I've got exactly what I want. Let's see if the space here needs that done to it as well. Nope. Okay, so after I finish this book, I can move on to these next books if I want to dive deeper into this. Let's see if I can find a free online copy of these. So here's Martin Fowler's website. Let's see if he's evolutionary design. That sounds interesting. Is design dead? Design sounds like it might be dead. I wonder why this guy is asking that question. It almost sounds as if he's asking it because design is dead. But an evolutionary architecture, like, that sounds better. Because then, like, you know, it's survival of the fittest. If you have an architecture that's because a lot of, because then it doesn't depend on your architecture being a certain way. Like, basically you're not saying that your architecture must look like this, this, and this because of this, this, and this. It's just all about what makes it go vroom. And that's what I'm all about, is having the code go vroom. That's the biggest thing for me. So an evolutionary design is just all about that, you know, survival of the fittest. If you go vroom the best, then you succeed and you propagate forward. So I'm pretty interested in that. So let's see here. So, okay. Now this is Eric Evans, but here's Martin Fowler. So, see, have yeah, I don't know. Let's try it. Let's try this. Oh, here we go. PDF. Here we go. Here's a ebook on it. Okay, so here's oh, this is by somebody else. This isn't by Martin Fowler. But here we go. Domain-driven design. This actually looks like a link to the book here. Yeah. So this looks like a blue book. Domain-driven design, tackling complexity in the heart of software. Let's see if that's. I mean, that's an older book. That's from 2003. I'd rather not read such an old book. Yeah. This is really interesting. I'm gonna put this in my further reading, but I'm not gonna read this right now. But that's definitely the kind of design I would want. It's just a design that only focuses on what is the best thing that you can do right now, and if there's something better, that's totally fine. All that's going to happen if there's something better is that this thing that we're doing now is just going to go away, and the thing that's better is going to be the thing that's going to be used going forward. As opposed to, is this thing designed in a way that we think the design should be, regardless of if that design is right for the current situation. And as we're going forward, we try to manipulate that situation to fit into this design somehow, and it just never quite works, and we're just always kind of off kilter with what is actually needed by this code. This is definitely the book. Yeah, and this is by Eric Evans. So I think I found it for free. This is the book that I found for free. Oh, and it looks like I've got two. Yeah, I've got two. I got it listed down here twice. So let's delete this. We're going to put it like that, and then we're going to link to it. There we go. And now we've got that saved. If we want to do further reading, we've got a copy of the full book. Looks like it was in 2003, so it might be a little bit out of date. We might not actually go through and read this. We might instead learn about evolutionary software design. So it is in the mundane world. So it is in the mundane world of business. It is that is that you start to use more complex and precise words and processes as you learn more and more about your current situation. The terminology used by business stakeholders represents a distilled understanding of the domain model, where complex ideas and processes are boiled down to a single word or phrase. When we hear, and often that is an acronym. So, like for a good example of that is DDD, which stands for Domain Driven Design. Like these are oftentimes your first few weeks on the job will be just learning what all these acronyms are that are being thrown everywhere. And that's because these are really complex ideas and processes built up over time, and they need to be referred to in a really concise way. And there's really no other way to refer to them than a custom made-up word, because they're so specific to the current situation. When we hear our business stakeholders using unfamiliar words or using terms in a specific way, we should listen to understand the deeper meaning and encode their hard-won experience into our software. We're going to use a real-world domain model throughout this book, specifically a model from our current deployment. MADE.com is a successful furniture retailer. This is the site the authors of the book made, and this is where they've got their experience from. They wrote this book after working on this project, and everything they learned from working on this project is a part of this book. And that's cool, because this is a pretty snappy site. I don't think I need anything. Oh, actually I do need like a bedroom chair, or like I need a chair. Let's see here, what kind of chair do I need? Definitely like a fabric, like because I need to I don't know. I definitely need a chair, but like this one looks like, yeah, this would be perfect. This is the chair I need. Oh man, it's so steep though. So steep. I don't know. I don't know how I feel about no arms. I definitely need arms. This would be like absolutely perfect. Yeah, this is basically what I need. Because basically I just want to do, I want to like read more books. So I like need a place to go and like sit down where like I can read a book. This looks good. This would be perfect. But I don't know. I'd have to try it before I buy it. I'm kind of apprehensive about trying a chair online just to realize it's the wrong chair for me. We source our furniture from manufacturers all over the world and sell it across Europe. When you buy a sofa or a coffee table, we have to figure out how best to get your goods from Poland or China or Vietnam and into your living room. At a high level, we have separate systems that are responsible for buying stock, selling stock to customers, and shipping goods to customers. A system in the middle needs to coordinate the process by allocating stock to a customer's orders. See context diagram for the allocation service. Okay, so we got here we go. So here's the diagram they had before, but it's filled out. So let's go and duplicate this tab. Now let's look at the basic, so here's the basic model. So we're gonna shrink this down and take a screenshot of it. All right, and then let's put this side by side with what they have here. So we can see it looks quite a bit different, but let's see, follow this. Let's follow this. So we've got a person here. They're a buying team. They need to purchase furniture from suppliers. So this is not the customer. This is somebody working for the company to make sure that when the customer buys a piece of furniture, it is available for them, and that the company makes a profit on that furniture when the customer gives them money for it, so that they pay less for the furniture than the customer pays. Okay, so the uses are, now here's a system, a purchasing system, and this manages workflow for buying stock from suppliers. So here's where you can keep track of what you paid for the furniture, the amounts that the suppliers are going to sell you, so you know, oh, I can't sell 10 of these to customers because I was only able to get 5 from my supplier, that sort of thing. So this purchasing system notifies about shipments. So another system will be for allocation, and it allocates stock to customer orders. So in addition to knowing how many you got from your supplier, you also need to know how many you were sold, so that you don't accidentally sell extra, or that you sell all of the ones that you have. All right, so the next step, it sends instructions to another system, and this is the warehouse, which manages workflow for shipping goods to customers. And then last, it dispatches goods to a person, the customer, who wants to buy the furniture. Now that's interesting. Does the customer get the furniture and then sends it back if they don't like it, or like? I guess I don't understand. So I guess the customer. Oh, you know what? I guess you can start it from either or. You can start it from here, or you can start it from here. You start as the customer, then you buy from the e-commerce site, and then you as the customer tell the system what you want, and then it goes like this. So, and then you can, so your e-commerce system will ask your allocation system. Do I have enough stock to sell it? And it will also say, hey, okay, I do have enough stock, so now the customer is going to buy this, so now you have less stock than you had before. So yeah, a really good, clear chart. This is the kind of thing I hope to be able to include with my programming projects. Right now, I'm just not used to drawing these charts, and even if I were to draw one, I don't know how to make it useful for me, and how drawing one could lead to better code. But I see now, I see from this how that could happen. You can differentiate between, you can see like what you actually need to put in to code. You don't need to put a person into your code, but you do need to process what this person does. So the customer will buy, the buying team will actually be using this system, so you'll need to create like a portal for the buying team. Here, of course, you got to make a portal for the customer, so you can have a better understanding of what kinds of inputs and outputs your code will process. For the purposes of this book, we're imagining that the business decides to implement an exciting new way of allocating stock. Until now, the business has been presenting stock and lead times based on what is physically available in the warehouse. If and when the warehouse runs out, a product is listed as out of stock until the next shipment arrives from the manufacturer. Here's the innovation. If we have a system that can keep track of all our shipments, and when they're due to arrive, we can treat the goods on those ships as real stock and part of our inventory, just with slightly longer lead times. Fewer goods will appear to be out of stock. We'll sell more, and the business can save money by keeping lower inventory in the domestic warehouse. But allocating orders is no longer a trivial matter of decrementing a single quantity in the warehouse system. We need a more complex allocation mechanism. Time for some domain modeling. This is really interesting because this is, from what I understand, like this is one of the problems the United States had in the pandemic, is like all of their systems were set up this way. So like everything like for like PPE, masks and stuff was created on demand like this, and in flight. So where all of a sudden you had an explosion of demand for it. In a prior kind of system, you would have kind of a stockpile more. But this system, basically, you don't need a stockpile anymore because it's just constantly churning in a continuous way. So once you have so then you kind of take away the incentive for a stockpile, because the stockpile just kind of ends up like wasting you money. And then you kind of take away the incentive for like having multiple manufacturers too, because they're not like integrated into your system or something. I guess I'm just making up that second part, but let me Google on that. So oh, there's so much. It's so hard to keep track of. It's so hard to keep up to date with everything. I used to follow it really really closely, but there's just a lot. I guess this one looks interesting. Supply chain. Oh, here we go. Here's a good one. Rethinking the global supply chain. Yeah, there's like a push for like reshoring jobs because like this type of um, flow like doesn't allow for uh, like uh, like there's a problem with it, but I don't know what the problem is. I think it'll tell me. Yeah, so right now commercial decisions are based primarily on low cost production and sophisticated logistics. So yeah, that's the problem is if you have sophisticated logistics that depend on a lot of things, when you have something like a pandemic, a lot of those things go wrong. So then all of a sudden uh, you're kind of left high and dry. Yeah, so you've got to, because the customer needs change so fast during a pandemic, you've got to be more agile in that response. So like if you're just using low cost production from China, you've got to ship it over and like, you know, it's, if you only rely on that and there's a problem, you know, you can't, it's going to take you a while to produce it in a different way, and it's probably going to cost you a lot to produce it. So it looks like 32% of global CEOs are rethinking their supply chains to become more agile in response to changing customer needs. 22% are rethinking their supply chains to become more robust in the event of a natural world disaster. I'm surprised that's so low. 19% are trying to bring their production closer to home to reduce the sophistication of their logistics. 10% are trying to reduce their supply chain risk exposure, and then 9% are pressuring governments through lobbying and stuff to try to bring production closer to home. And this is global, so they're pressuring their governments in whatever country they happen to be based in. That's interesting. Yeah, and that's kind of what I thought. Like, right now, a lot of businesses are set up like this, where like logistics are like really complicated, but like manufacturing or like production is like really cheap and efficient. So if there's a problem with your logistics, things just all fall apart. So like things are kind of too far set up that way, where it depends on sophisticated logistics a little bit too much. So a lot of CEOs are kind of rethinking how they can blend more, how they can depend less on sophisticated logistics. I mean, I think one of the ways you could do that is just like if you're GE, or like General Electric, basically like, because there's, I don't know like what the laws are, but like, yeah, I mean, I was gonna say like you could like purchase manufacturing from like another company that's like onshore, and then you can have it be kind of like cloud services where it's like on demand, and you can say, okay, we're doing it in China because that's the most efficient and that's the lowest cost, and we're depending on our complex logistics. Oops, something happens, some idiot sunk a giant tanker in the middle of a canal that happened recently. So now, we've got a contract with these guys. We need you to deliver for us. That seems like a way to do it. But I'm not sure, like, if you have something that's just the kind of pops up, kind of like the cloud services. I guess you would always have an instance globally where there was demand. But like kind of having a recurring, persistent business relationship seems like it would be a bit of a hindrance, and just kind of having pop up, sporadic, like, oh, I need this now, can you give it to me? Business relationships, and then of course you have the long-term, deep relationships as well, but those are with areas like offshoring, where you get the lowest cost and the most efficient, but just with the most complicated logistics. Like having a way to on a dime switch and have the least complicated logistics with the highest possible cost would be an awesome way to do it. Like even just putting out like a pop-up job, like, and then you have all these pop-up jobs everywhere where it's like, we're a business, we make shirts in China, we offshore in China, we have complicated logistics modeling, all that comes in. Oops, there's a pandemic now, we can't do this the same way we did, so we've got funding, we're gonna pop up our own production in this area, we're going to hire people massively on 6 months, year contracts, and they're gonna come in and do this work just right in this area, and anyone who wants to come and make money can come and do that, and we'll actually pay them a lot because we'll save a lot in our logistics. We basically won't have to pay anything for that. But that's just me speculating. I'm not a CEO, so I have no idea. Okay. Okay, so here's the innovation. If we have a system that can keep track of all our shipments, and when they're due to arrive, we can treat the goods on those ships as real stock and part of our inventory, just with slightly longer lead times. Fewer goods will appear to be out of stock and will sell more, and the business can save money by keeping lower inventory in the domestic warehouse. But allocating orders is no longer a trivial matter of decrementing a single quantity in the warehouse system. We need a more complex allocation mechanism. Time for some domain modeling. Exploring the domain language. Understanding the domain model takes time and patience and post-it notes. We have an initial conversation with our business experts and agree on a glossary and some rules for the first minimal version of the domain model. Wherever possible, we ask for concrete examples to illustrate each rule. We make sure to express those rules in the business jargon, the ubiquitous language in domain-driven design terminology, ubiquitous. We choose memorable identifiers for our objects so that the examples are easier to talk about. The following sidebar shows some notes we might have taken while having a conversation with our domain experts about allocation. Some notes on allocation. A product is identified by a SKU, pronounced SKU, which is short for stock keeping unit. Customers place orders. An order is identified by an order reference and comprises multiple order lines, where each line has a SKU and a quantity. For example, 10 units of red chair, 1 unit of tasteless lamp. When purchasing department. Oh, the purchasing department orders small batches of stock. A batch of stock has a unique ID called a reference, a SKU, KU, and a quantity. So it's a SKU, it's a stock keeping unit. We need to allocate order lines to batches. When we've allocated an order line to a batch, we will send stock from that specific batch to the customer's delivery address. When we allocate X units of stock to a batch, the available quantity is reduced by X. For example, we have a batch of 20 small table and we allocate an order line for 2 small table. The batch should have 18 small table remaining. We can't allocate to a batch if the available quantity is less than the quantity of the order line. For example, we have one batch of 1 blue cushion and an order line for 2 blue cushion. We should not be able to allocate the line to the batch. We can't allocate the same line twice. For example, we have a batch of 10 blue vase and we allocate an order line for 2 blue vase. If we allocate the order line again to the same batch, the batch should still have an available quantity of 8. Batches have an ETA if they are currently shipping, or they may be in warehouse stock. We allocate to warehouse stock in preference to shipment batches. We allocate to shipment batches in order of which has the earliest ETA. Unit testing domain models. We're not going to show you how test-driven development works in this book, but we want, oh, well, I thought they were, god damn it. That's why I got this book. But we want to show you how we construct a model from this business conversation. I think they mentioned that earlier, that they're actually not going to go deep into detail about test-driven development. And if you want to learn kind of the details of it, you need to read another book. I think they mentioned that earlier, which is totally fair. And that's kind of what I want to some extent, is just kind of help with like, where do I go to get good at this stuff? And this is probably one of the, okay, well, that's interesting. I don't see, interesting. Okay, so exercise for the reader. Okay, so we're not going to show you how test-driven development works in this book, but we want to show you how we would construct a model from this business conversation. Oh, perfect. Exercise for the reader. Why not have a go at solving this problem yourself? Write a few unit tests to see if you can capture the essence of these business rules in a nice, clean code. You'll find some placeholder unit tests on GitHub, but you could just start from scratch, or combine/rewrite them however you like. Here's what one of our first tests might look like. So for this one, we're going to test allocating to a batch reduces the available quantity. Okay, so for my test, one of the first tests I'm gonna want to do is actually ping the device. Yeah. I mean, before that, I've got to feed it a DHCP. So we're gonna be basically like flooding the topology with DHCP packets, DHCP broadcast traffic, which is why STP is super important. Oh, what the heck? Do I already have one open? Looks like the project closed. Yeah, the project closed. Well, my device is shut down too. That's okay, I'll circ them all up again. Okay. So, one of my first tests, so here they're going to assert that a batch has a available quantity, but we don't need to make an assertion like that. I guess what we can do is we can assert that a IP address is a certain value. The name of our unit test describes the behavior we want to see from the system, and the names of the classes and variables that we use are taken from the business jargon. We could show this code to our non-technical coworkers, and they would agree that this correctly describes the behavior of our system. Here is a domain model that meets our requirements. Okay, so we've got data class frozen equals true. That's interesting. What is data class? I don't know. Yeah, I'm confused by this. I'm already lost. Number one, the order line is an immutable data class with no behavior, and it's got a decorator. I don't really understand decorators too well. Number two, well, why is it there? Oh, it looks like it's being used. Wait, no it's not. Yeah, why is that there? I don't know. I'm confused. Number two, we're not showing imports from most code listings in an attempt to keep them clean. We're hoping you can guess that this came via from data classes import data class. Likewise, typing.optional and datetime.date. If you want to double check anything, you can see the full working code for each chapter in its branch. Type hints are still a matter of controversy in the Python world. For domain models, they can sometimes help to clarify or document what the expected arguments are, and people with IDEs are often grateful for them. You may decide the price paid in terms of readability is too high. What's a type hint? Is this a type hint? I don't know. Our implementation here is trivial. A batch just wraps an integer available quantity, and we decrement that value on allocation. We've written quite a lot of code just to subtract one number from another, but we think that modeling our domain precisely will pay off. Let's write some new failing tests. There's nothing too unexpected here. We've refactored our test suite so that we don't keep repeating the same lines of code to create a batch and a line for the same sales something unit, SKU, SKU. Oh, stock keeping unit. We're trying to determine how much stock we need. And we've written forcible tests for a new method, can_allocate. Again, notice that the names we use mirror the language of our domain experts, and the examples we agreed upon are directly written in the code. We can implement this straightforwardly too by writing the can_allocate method of batch. So far, we can manage the implementation by just incrementing and decrementing batch.availableQuantity, but as we get into deallocate tests, we'll be forced into a more intelligent solution. In this test, we're asserting that deallocating a line from a batch has no effect unless the batch previously allocated the line. For this to work, our batch needs to understand which lines have been allocated. Let's look at the implementation. Our model in UML shows the model in UML. I don't know what UML is. Now we're getting somewhere. A batch now keeps track of a set of allocated order line objects. When we allocate, if we have enough available quantity, we just add to the set. Our available quantity is now calculated properly. Purchased quantity minus allocated quantity. There's plenty more we could do. It's a little disconcerting that both allocate and deallocate can fail silently, but we have the basics. Incidentally, using a set for _allocations makes it simple for us to handle the last test because items in a test are unique, or in a set are unique. So, where's the set? There is no set. I don't see the set. Oh, here we go. So it looks like allocations that add. You can add to and remove from sets. At the moment, it's probably a valid criticism to say that the domain model is too trivial to bother with domain-driven development or even object orientation. In real life, any number of business rules and edge cases crop up. Customers can ask for delivery on specific future dates, which means we might not want to allocate them to the earliest batch. Some stock something units, I forget. Oh, stock keeping unit. Some stock keeping units aren't in batches, but ordered on demand directly from suppliers, so they have different logic. Depending on the customer's location, we can allocate to only a subset of warehouses and shipments that are in their region. Except for some stock keeping units, we're happy to deliver from a warehouse in a different region if we're out of stock in the home region, and so on. A real business in the real world knows how to pile on complexity faster than we can show on the page. But taking this simple domain model as a placeholder for something more complex, we're going to extend our simple domain model in the rest of the book and plug it into the real world of APIs and databases and spreadsheets. We'll see how sticking rigidly to our principles of encapsulation and careful layering will help us avoid a ball of mud. More types for more type hints. If you really want to go to town with type hints, you could go so far as wrapping primitive types using typing.newType. This would allow our type checker to make sure that we don't pass a stock keeping unit where a reference is expected, for example. Whether you think this is wonderful or appalling is a matter of debate. Data classes are great for value objects. We've used line liberally in the previous code listings, but what is a line? In our business language, an order has multiple line items, where each line has a stock keeping unit and a quantity. We can imagine that a simple YAML file containing order information might look like this. Notice that while an order has a reference that uniquely identifies it, a line does not. Even if we add the order reference to the order line class, it's not something that uniquely identifies the line itself. Whenever we have a business concept that has data but no identity, we often choose to represent it using the value object pattern. A value object is any domain object that is uniquely identified by the data it holds. We usually make them immutable. So I don't know, does this make it immutable? I've never seen this syntax in Python. Maybe this frozen equals true is what makes it immutable. One of the nice things that data classes or named tuples give us is value equality, which is the fancy way of saying two lines with the same order ID, SKU, and QTY are equal. Oh, okay. So you can find a bool on it or something? Yeah, so okay, so you can have okay. These value objects match our real-world intuition about how their values work. It doesn't matter which 10-euro note we're thinking about because they all have the same value. Likewise, two names are equal if both the first and last names match. And two lines are equivalent if they have the same customer order, product code, and quantity. We can still have complex behavior on a value object though. In fact, it's common to support operations on values, for example, mathematical operators. To get those tests to actually pass, you'll need to start implementing some magic methods on our money class. So this is what a magic method is. Now this is called a I don't remember. I'm going to look it up. Oh, it's called a dunder. I remember now. So it's the add dunder. So a dunder means these two underscores at the beginning and the end. An easier way to say that is to call it a dunder. So this is an add dunder, which is a magic method. Magic methods are written using dunders, and a dunder is just any function name beginning and ending with two underscores. Those are called dunders. Value objects and entities. An order line is uniquely identified by its order ID, stock keeping unit, and quantity. If we change one of those values, we now have a new line. That's the definition of a value object. Any object that is identified only by its data and doesn't have a long-lived identity. What about a batch though? That is identified by a reference. We use the term entity to describe a domain object that has long-lived identity. On the previous page, we introduced a name class as a value object. If we take the name Harry Percival and change one letter, we now have a new name object, Barry Percival. It should be clear that Harry Percival is not equal to Barry Percival. But what about Harry as a person? People do change their names and their marital status and even their gender, but we continue to recognize them as the same individual. That's because humans, unlike names, have a persistent identity. Entries, unlike values, have identity equality. We can change their values and they are still recognizably the same thing. Batches, in our example, are entities. We can allocate lines to a batch or change the date that we expect it to arrive, and it will still be the same entity. We usually make this explicit in code by implementing equality operators on entities. Python's EQ dunder magic method defines the behavior of the class for the equal operator for both entity and value objects. It's also worth thinking about how hash dunder will work. It's the magic method Python uses to control the behavior of objects when you add them to sets or use them as dict keys. You can find more info in the Python docs. For value objects, the hash should be based on all the value attributes, and we should ensure that the objects are immutable. We get this for free by specifying at frozen equals true on all the data class. Okay, that is how they made it immutable. For entities, the simplest option is to say that the hash is none, meaning that the object is not hashable and cannot, for example, be used in a set. If for some reason you decide you really do want to use set or dict operations with entities, the hash should be based on the attributes such as .reference that defines the entity's unique identity over time. You should also try to somehow make that attribute read-only. Warning, this is tricky territory. You shouldn't modify dunder hash without also modifying dunder EQ. If you're not sure what you're doing, further reading is suggested. Python hashes and equality by our tech reviewer, Heineck Schlaulich, is a good place to start. I'm interested where this person is from, because from what I, they're from like Germany, because from what I understand, this like SCH is like local to like a region in Germany, because my last name has SCH in it, so like this is like this person probably looks like me. He appears to kind of look like me. All right, so here we go. So let's see what kind of articles this person has. Semantic versioning. Let's put this in the further reading. But at the same time, like, I don't want to change any of the plumbing of Python. That just doesn't interest me at all. I don't understand why I would have to do that, so I'm really not that interested in that article. Okay, so we're at the 144 mark. We've still got a lot to go through. I didn't do any of the examples or anything yet. I don't know. I'm trying to figure out how I can do that, but this is going to be the end of the video for now. It's just been going too long for me to maintain focus on. I need a bit of a break, so I'm going to update my bookmark here. Hit up. Let's update it one more time. Yep, and then we're going to hit that. Apply. We're going to test it out. Okay, so we've got the bookmark looking good. Update, check it one more time, just because I'm worried it will go away and I won't know where I was. Yeah, so that's it. We learned about the dependency inversion principle. We learned some of these key design patterns. It's kind of all over my head right now, and I apologize. I did skip all of these examples. I probably should write them out character by character and get a better sense for them, or actually go and try to write some relevant to what my code along project is going to be. You know what? I think I'll probably be doing that a bit in the next video. So thanks for watching, and see you in the next one.